Yeah, thank you. So I'm going to talk a little bit about particle characterization with digital holography. And this is work I've been doing for a while now, but lately with my graduate student, Nava Subedi at Mississippi State University. So generally, the background and motivation here is our group is trying to characterize large aerosol particles. So particles we say that are in the coarse mode. And we want to do this in particular in situ. We don't want to collect these particles and look at them under a microscope, although we could do that, because we don't want to disturb their physical form. And in particular, we're interested in the particle size and the particle shape. Now, as you know, a common approach to do this is to measure, say, the scattering pattern in one dimension or two dimensions. And you could also perhaps measure the scattering matrix elements or an integrated quantity like the cross-section. And here's an example of work from Kevin Aptowitz showing the two-dimensional light-scattered intensity distribution collected from a single urban aerosol particle. And the thing to notice here is the complexity of this pattern. And to interpret this pattern and try to invert it, if you will, to extract the information to do this characterization is an extremely challenging task. Again, we know this. And there is no general inversion technique possible. This is the basic idea behind what's called the inverse problem. So a while back, we started looking at some alternatives to do this characterization, but also retain the benefits of scattering. And digital holography turned out to be the way to go. So to explain briefly how this works, suppose we've got a laser beam and we expand it and then let it fall directly onto a two-dimensional detector, maybe a CMOS or CCD detector. Now, if there's no particle here, then we simply are going to get basically the beam profile of the expanded beam on the detector, or the incident field, the intensity of the incident field is what we'll measure. So I'll call this a background or reference measurement because I'm going to do something with it in a minute. Maybe we have some noise or some rings from the lenses or something here, but largely this is just the beam profile. Okay, now if we let a particle show up in front of the detector, notice we've got two waves. We've got the incident wave we had before, and now we've got the particles forward scattered wave. And of course, the two will interfere across the detector, and the result will be an interference pattern we now see. Okay, so here's a particle. I'll tell you what it is in a minute, but you can see it produces a very complicated interference pattern. And indeed, this is essentially as complicated and unintelligible as the scattering pattern is. But encoded in this interference pattern, though, is phase information, and that will turn out to be critical. So before we do anything more with this, what we'll do is take the difference between that reference or background measurement we did when there's no particle present. We'll subtract from it the interference pattern we measure when the particle is present. And this gives us a difference measurement we call the contrast hologram. Okay? This background subtraction really serves the purpose to eliminate a lot of the noise present in the beam and will subsequently improve the characterization of the particle. Yeah, and I guess I already said this. Note that this is, again, a very complicated pattern. So what can we do with it? Well, we can apply the Fresnel-Kirchhoff diffraction equation or integral to this contrast hologram, and the result will be an image of the particle. And if you want to think about this in a physical sense, it's basically, if we think of, instead of having a CCD camera, we had a photographic plate, and we recorded the interference pattern produced by the particle on that plate, developed the plate. It basically turns into a transmission diffraction grating. Stick that back in the original beam and let the light go through it with no particle present, and the light will diffract down to form an image of the particle at this distance d, which represents the original particle film plate separation distance. Okay? So it's like diffraction imaging, except we can do it in computer land with the Fresnel-Kirchhoff diffraction interval. Okay. Before I show you how that turns out, this is one of our early setups to try and actually demonstrate the concept. Basically, we draw an aerosol in here through this aluminum tube. This may be a sand aerosol or a pollen aerosol, something with big particles. And it's in a flowing stream. And the particles in the stream pass through the intersection of these two different colored laser beams. This is the cross beam trigger that Pon was referring to a minute ago. Basically, they're slightly different colors, and so if a particle hits the intersection, then it scatters both colors simultaneously, and we register a coincidence signal from these PMTs. And that then allows us to fire this green laser right when the particle's in the desired location. And the green laser is what we use to form, or to record to form the hologram on this CCD detector, this black box right here. So the point of showing this is that it's actually a pretty simple optical arrangement as far as these experiments go. And indeed could be miniaturized much more than what I built there. Okay, so anyways, there's that contrast hologram I showed you. Now, I told you if I apply the Fresnel-Kirchhoff diffraction integral to this, you can get an image of the particle. So doing that, we get the following. And you can see that, okay, well, I don't know what the particle is here, but if I do the diffraction integral, reconstruct an image from the hologram, it's obviously a cluster of spherical particles. And indeed, this was a ragweed pollen cluster, or a ragweed aerosol. And if you know what ragweed looks like, they're basically spheres with spikes on them. They tend to interdigitate and stick together. And so you actually would expect to see clusters of these particles in an aerosol if it's concentrated enough, which it was in this case. Okay, so this is successful as an imaging characterization. A couple of other examples here. Here's a Saharan sand aerosol, so a Saharan sand particle hologram. Reconstruct an image, and you see you get a nice blob, potato-shaped looking sand particle. Again, it's pretty big because we're in the coarse mode. And then lastly, the Tunisian sand. And you can tell right away that there's vastly different morphologies between these two particles, but you wouldn't have been able to say that in any general sense if I only gave you the contrast holograms. Okay, fine. So we can use holography to look at the shape and size of particles, but it turns out, this is our more recent work, that there's a whole lot more information contained in the contrast hologram than just the morphology. And in particular, it relates to the extinction cross-section of the particle. So before I get into how that works, let me remind you what I mean by extinction cross-section. Suppose we've got a two-dimensional detector again, something like a CCD detector here, and it's facing an incident collimated beam, and there's no particle present. So the detector then is just going to measure an integrated total amount of power that it receives, and so some number on the dial here. Well, but if I put a particle in the way, we know we're going to get absorption, and we're going to get scattering to varying extents, and this is going to cause extinction and reduce the amount of power reaching the detector. Okay, this is the basic idea behind extinction, and of course we can calculate how much power is scattered, how much is absorbed. The sum of the two then gives us the power extinguished by the particle. But the thing to notice here is this scenario is essentially exactly the same measurement I told you about to measure the contrast hologram for a particle. You start with the background measurement, i.e. a measurement with no particles present, and then you let the particle show up and you repeat the measurement. And you take the difference between the two. That gives you the contrast hologram. The only difference here is you integrate across the whole detector to get a net amount of power that it receives, and then you are able to calculate the extinguished power. So this suggests that there's a formal connection between extinction, or the extinction cross-section, and the integral of a contrast hologram. And indeed, we can make this description a little bit more formal. Starting with Poynting's theorem, the power absorbed by a particle, I mean, this is a very general treatment at the moment, is given by the negative integral of the divergence of the time average Poynting vector, evaluated over some arbitrary volume that encloses the particle. Okay? So typically what one will do then is apply the divergence theorem to that integral to transfer the volume integral onto the surface of an imaginary surface that encloses the particle. Okay? Typically, we choose a large spherical surface centered on the particle to do this integral. And often we choose that spherical surface to be so large that it lives in the far field of the particle, and the fields are simpler, and the integral is doable in many cases. But the divergence theorem does not require you to do that. You don't have to choose a spherical surface. So perhaps we could choose something a little bit more suggestive. For example, suppose I've got a particle here, and I'm illuminating it with an incident wave, and then here's my hologram detector. Okay, so the situation we've been looking at so far. Now, this surface I'll apply the divergence theorem to and evaluate Poynting's theorem over is a large spherical surface centered on the particle, except we indent the right-hand side of the spherical surface so that it becomes a planar disk that's coincident with the surface of the detector. Okay? Still forms a closed surface, so I'm allowed to apply the divergence theorem. I'll call the spherical part S1 and the planar part that lives on the detector S2. Okay, with that in mind, then, Poynting's theorem boils down to the absorbed power is equal to the sum of these two surface intervals. All right, fine. Well, let's keep going. Now remember that I told you measuring extinction tacitly requires us to compare two scenarios. When there's no particle present and when there is a particle present. So I'll define two quantities. The first one, this script I detector knot, is just the integral of what the CCD camera sees when there's no particle present, which mathematically is the integral over that disc-shaped surface S2, coincident with the detector, of the incident energy flow. Okay? Then I'll do exactly the same calculation, but the particle is present now. In other words, this is the integral of our raw hologram before we do the subtraction to get the contrast hologram. It's the integral over the detector surface S2 of the total Poynting vector now. Okay, now lastly, let's take the difference between these two calculations. That gives me this script I con, or contrast integral, if you will. What does that equal if we do some algebra and expand it out? Well, after you do that, and I'm skipping a lot of steps here, but you can show, and again, there's no approximations yet, that difference between those two quantities is equal to this mess. But notice that the terms in this mess have some physical significance. First of all, we have a term that is the total scattered power of the particle, which is related to its scattering cross-section. We have a term over here, which is the total extinguished power of the particle, related to its extinction cross-section. And then we have these two integrals. So if we imagine evaluating this difference quantity, but we do it as we change the size of this surface S2 from being no surface at all, so we have a complete spherical surface for S1, to growing it until it eats up the whole detector, and we quantify that by varying this angle, theta detector, then we can look at the behavior of these two integrals, and what we'll find is the following. When S2 is small and we have nearly a complete spherical surface for S1, this term here gives us almost, to good approximation, the scattered power due to the particle. And so it gets knocked off by this term here. In other words, these two terms will tend to cancel each other. This term here, the integral around the spherical surface of the energy flow due to the interference of the incident and scattered waves, tends to be zero on average because it oscillates rapidly from inward to outward in direction as you go around the spherical surface. So this integral you can think of on average as being zero or neglecting it. Then at the end of the day, this difference quantity that we calculate is basically equal to the extinguished power. Okay? But notice that the left-hand side of this integral, this difference quantity, is essentially just the integral of your contrast hologram as a function of this theta detector angle. Okay, so that may sound a little sketchy, but I can show you that it works out. So what we did is we did some supercomputer simulations using DDA, and then compared that, also used T-matrix to simulate some holograms. So in the first case, I'm showing you a spherical particle about the size of a wavelength with the refractive index of water at around 532 nanometers. And this is a DDA simulation of the contrast hologram you'd expect. All right, fine. So I got the contrast hologram for this particle now. And then if I calculate this difference quantity, this icon that we were just talking about, as I vary the size of this S2 according to theta detector, I'm going to get a curve that oscillates wildly. Okay? What I'm plotting here is not just I contrast, but it's I contrast divided by the extinction cross-section of the particle, which I know because I'm in simulation world here, right? Now, as you start increasing the size of S2 and integrating more and more of your contrast hologram, this curve oscillates rapidly, like I said, but notice that the average of the curve hits 1 here. So the average of the integral of the contrast hologram gives you, to good approximation, the extinction cross-section of the particle. Okay? And then as you integrate more and more of the detector, this thing asymptotically will go to 0. All right, well, that was for a simple case, a single sphere. Oh, by the way, we compared this to T-matrix to make sure that DDA was behaving properly, and it was. But now that we have DDA and it's working well for this problem, we can apply it to more interesting cases. Like here's a cubical particle that's about twice the size in terms of volume equivalent radius of the sphere I just showed you, and it's in the highest symmetry configuration, where the polarization of the incident field would be like that, parallel to its bases, coordinate spaces. Anyways, and so we do this calculation. We integrate the contrast hologram again, and we see the same result. We get a highly oscillatory curve, but the average of the curve hits 1 on the vertical axis. So the average of the curve, even the cube, gives us the extinction cross-section. Okay. Make things a little bit more interesting now. Now a highly absorbing cubical particle, and I'll break the symmetry. And you see, the same conclusion still applies. So absorption doesn't spoil this effect. What it does do, though, is absorption, as you'll notice, no absorption, absorption, causes the tail to kick up. And I haven't proven this yet, but I think that the asymptote here is related to the particle's absorption cross-section. Stands to reason. But anyways, the lesson here is that you still have this conclusion that you can measure the extinction cross-section by integrating a contrast hologram. Okay, so this brings us to an overview of what you can get from digital holography in the context of aerosol particle characterization. From this single measurement, which can be made with a single laser pulse in 35 nanoseconds on flowing aerosols, you can get the size of the particle, you can get its shape. Right there, in some operational sense, we've solved the inverse problem. Okay? Now, I've just shown you that to some approximation, say 1 or 2% error, or maybe 10 at worst, you can get a measurement of the extinction cross-section of the particle. We're working on a way where we think we can also get the scattering cross-section of the particle from this same single hologram. Then from energy conservation, that gives us the absorption cross-section and the single scattering albedo, simultaneous with all these other quantities. So this is building towards a complete description of a coarse mode aerosol particle. So what is needed in the context of this workshop? Well, yeah, coarse mode particles are important in their own right, but we would also like to apply this to the fine mode, which at the moment is not possible due to the resolution limits of essentially the hardware and the diffraction limit. So we would like to push this resolution to 1 micron or smaller, but that will probably require some improvements in the hardware before that can be realized. However, other things to think about here, like can we incorporate material composition information in this process here? Can we extract some information related to the material of the particle from the hologram? Because as it stands now, we just get silhouettes. Could polarization-sensitive hologram measurements yield useful information? For example, in maybe finding the particle phase, something like that. And probably most important, we're going to build this into a black box and take it out into the farm fields in Mississippi, and we're going to try and map out quantitatively the real atmospheric aerosol shape distribution. So we have a way we think we can describe shape in a general sense, rather than, well, I guess that's all I'll say on that at the moment. But okay. Fine. So if you're more interested in the technical details, there is an optics letter out last year that covers this, and it's freely available on our research website. And thanks to ARO and NSF for funding this.